Good afternoon, everyone. It's my pleasure to introduce our speaker for today, Professor Michael Prather. He needs no introduction, but I'm going to introduce him anyway. Michael earned undergraduate degrees in mathematics at Yale and physics at Oxford, and a doctorate in astronomy and astrophysics at Yale. For almost 2 decades, he was a researcher at Harvard and Goddard Institute for Space Studies and a program manager at NASA headquarters. He was then hired as a founding faculty of our own UCI Earth System Science Department, where he's a distinguished professor and has been recognized for his contributions to UCI with a Lauds and Laurel Faculty Award and as a Kavli Endowed Chair. Michael's research at Harvard and NASA GIST for almost 2 decades was pioneering work in establishing our current fundamental understanding of both tropospheric and stratospheric chemistry. His research at UCI in the last 2 decades has changed how we think about atmospheric chemistry, greenhouse gases, and climate change on this planet, and has been critically important for establishing the scientific basis for identifying and mitigating climate change. To make sure that his science was making a difference, Michael has worked to apply it at UCI, including as director of the UCI Environmental Institute, and at the national level by serving in the US State Department as a Jefferson Science Fellow. At the international level, this includes his role as a lead author on multiple IPCC chapters that collectively were awarded the Nobel Peace Prize. You can see Michael's passion for this work on his license plate, so check it out when we're all back to campus. And now I'll turn it over to you, Michael.
Thank you, Alex. So it's really wonderful to be here in Crowell Hall and to be in the round room, as you can tell from the background. It's the beginning, we hope, of the end of isolation. So sooner or later, we'll get to a stage where we can all gather in one place. So my seminar will be a 30-some year history. It's basically about atmospheric chemistry. I think of it as a piecewise linear because it's going to be in sections that don't always connect. And we're going to be looking for the interesting parts. So the other title for this seminar is really this one. It's a wrinkle in space-time. It's for when you find the wrinkles in your science, you actually find some wonderful things. And so we'll be looking at cases where the wrinkles turned out to be one of the more exciting things you could ever imagine. It's like the dust under the rug. So for atmospheric chemistry, it always suffers from the outside community as being like too complex, too nonlinear. It's always given these pejorative descriptions. And generally the people who don't want to, often physical climate or other people involved, just don't want to understand it. So they sort of say it's just nonlinear or too complex and they want you to throw it away. Now, example of this is that in 2007, the IPCC had to backtrack on human cause of climate change because they went through this formal attribution. And you'll note the statement on the right is fairly contorted. It had to be changed in the review process, the government review process, because it was incorrect. Originally, it said due to human effects. And it turns out they had never actually done the assessment of whether the greenhouse gases were caused by humans. Now, we all know that, and we have done many studies on it, but the climate people did not put that in their attribution assessments. So they couldn't make the statement. They assumed that the increase in greenhouse gas was all human-driven. And so they had to backtrack. So I tried to, when a scoping meeting for the next IPCC report right after this one, I tried to explain to my colleagues, including Francis Weirs, who was in charge of the chapter on all this detection attribution, that really they should include some chemistry in there to find out whether or not, at what level, changes in methane are strictly anthropogenic or natural. And the attitude was mind-boggling. This is my interpretation of what he said. I'm trying to remember it, but atmospheric chemistry is not a developed science. It's not enough mathematical rigor. And I was sort of, imagine, left speechless even at this one. I sort of stared down and said, what? And left. And so there's an attitude still that's out there that atmospheric chemistry is just either not developed or too complicated, not sure which. So we're going to go for the mathematical rigor this time. So chemistry really does have nice clean rigor, okay? Chemistry involves 2 species that react. They react quadratically, X and Y. That means the Taylor expansion has a second order term, which is a second derivative with regard to X, Y, even if it's not species self-reaction, but two species make it in nonlinear chemistry. And that actually ends up making chemistry a lot of fun. So let's look at some of the math of how we set up the equations and solve them, because it'll be critical to some of the discoveries you'll see. So the core of chemistry really is a continuity equation. In a box, it's written as the rate of change is the production minus the loss. It could be truly linear, but usually production and loss depend on a whole range of species. The idealized operator, sort of first order time, is delta x over delta t, the change in time step delta t, is equal to some operator. Now, A is the random operator. It has chemistry, transport, radiation, and we can linearize it by perturbations around whatever state we're in. And so below is a simple Taylor expansion, and we see cross terms, we see second order terms, del second, del x second, we see cross terms, okay? And that's basically, if you want to think about chemistry, that's the linearization of it. So how do we solve it? We end up solving it often by using this linearization. And so what I set up is a set of equations to solve for the rate of change in x, y, and z as a function of the matrix. And that matrix is set up now on the bottom line as a matrix equation. And this is basically the equation we use. The middle matrix is called the Jacobian. That's critical. And we can always set the left-hand side to 0 and find out what the steady state solution is, but this is the equation we would use to solve for a coupled chemical system. The main thing about this Jacobian that's important is you generally want it to be mostly linear in the regime where you are. You want the perturbation, you want alpha over some solution, you want the size, the coefficients of the second order derivatives to be small, and you want this whole thing to be differentiable, that is smoothly varying. And if you don't have that, then you end up in trouble. So this was one of the first papers I ever did at Harvard. It's on stratospheric ozone. It has all these chemical rates. We draw all these boxes, make all these nice chemical things. We still do these silly symbols, schematic diagrams all over the place. We did all these calculations, okay, and we ended up having to use a supercomputer at Ames. Even though we're in Boston, we had to go across the country at that time. It was possible to do so in spite of the network being rather primitive, but it worked. We didn't have the computational power to even solve these equations. Now, one of the problems was getting things to converge. You have an answer, you're not quite there. And so when you have, you really need sort of numerical precision to find that you're actually solving the correct equations in the right way. So you want to converge on the iterations. So if you think about it, you calculate a first order correction, delta x, and let's say the change is 10. Second time you get something like -7, it starts bouncing around. Third time you get 1, then you get minus 2/10, then you get 0.1, 0.01, and 0.01. The last three are an example of what is quadratic convergence, which is what you should get when you solve these equations, as we described before. That's when you're in the regime of the right answer, and it converges very quickly and straightforwardly. And so that's what you're looking for. If you're in the first few places, you're bouncing around trying to find the correct answer, and you aren't near it. But if the Jacobian is not calculated correctly, like you make a mistake in it, which happens, we've done that many times, or if there are multiple solutions, or if the Jacobian, basically the matrix is nearly 0, then what you end up with is crazy oscillations. You start dividing by 0 effectively, and you end up with an oscillating solution that never quite converges, may eventually jump into the next country. So this is what you're looking for mistakes, and this is what you're trying to get rid of, and you want the blue convergence when you're running a chemistry model, not the red one. So what happened? After the 1978 paper, I was trying to solve for ozone loss in the polar winter, and we ran into all sorts of non-convergence problems like that red one. Exactly like that red mix, nothing would ever converge. And we finally sort of flipped the solution around and found out that we had multiple solutions, which meant there was more than one value of chlorine monoxide for a given value of total chlorine. So the partitioning, there were 3 different correct answers to the system. It truly was multiple solutions. This was great fun because nobody ever found this in atmospheric chemistry before. They'd done it in chemistry systems in labs, but nothing in the atmosphere. So we really had a bifurcating system with 3 solutions. This was fantastic and fun. It's my still favorite paper. It's a Geophysical Research Letters paper. You'll recognize it. It's only 2 pages. Okay. As a short abstract, it was submitted on December 27th, and over the holidays, it was accepted by January 16th. It's one of the fastest papers I've ever had. There are only 2 references. And it's rather nice to sort of, science can still be done this way. I'm not sure it still can be, but it was a great, fun achievement. So thereafter, what happens? Well, nobody believed us. So we shipped piles of computer output to Livermore, where Julius Chang, Joyce Benner, Don Webbles were working. And they tried as they couldn't reproduce it. We kept finding it, we could reproduce it. And so it was an issue like we weren't sure it was real. They didn't think it was real, we were. And we found out that it was actually a method of how you actually set up the model. So we found out that the model structure determined whether or not the multiple solutions existed. We solved our chemistry locally and finished it, and then added diffusion. Livermore integrated diffusion with the chemical solver. And for that, you need supercomputers, and they had them. And so it turns out when you have diffusion and mixing between levels, the whole multiple solutions disappears. So alas, it was sort of a reality check that, maybe the real world doesn't have these after all. But it was fun. So what's the follow-up? There's quite a lot of interesting, fun stuff that came out of that afterwards. White, Dietz, and Richard Stewart at Goddard and several others found a whole set of multiple solutions in the boundary layer using NO and CO. The system would oscillate between extremely high and extremely low ozone. It had strange attractors. It was a true multiple solution problem. Somebody also, Fickelman and someone, found similar behavior in the mesospheric chemistry with chaotic behavior. And so this is great fun. The problem was that if you looked at the middle one, to get it to work in the boundary layer, you had to have the boundary layer not being mixed with the atmosphere for over several hundred days. And that was not a practical solution. So it's like the one we found in the stratosphere. In the real world, none of it was there. So it was great fun. It was close. It was exciting for something really big, and it never panned out. So that wrinkle was fun, but disappeared. We did have fun. Jane Fox built a diffusion model, and we put blobs of multiple solutions next to each other. We found stable and unstable solutions. We still played with it for a while. It was quite interesting. But again, it was mostly a sort of toy exploration. But it did end up being the core for a Yale undergraduate, astronomy undergraduate, who my former thesis advisor sent to me to GIST to do work, Andrew Jaffe. The summer we built a chemistry diffusion type model to find out what would happen if the ozone hole broke up. Blobs from the ozone hole basically were carried out and mixed into the real atmosphere. Did they actually enhance the chemistry and destroy even more ozone than they found originally or not? So we built the model specifically to basically follow a highly perturbed ozone hole blob and put it in mid-latitudes and find out what happened. And the answer was there was no additional ozone loss other than the loss it carried with it. So it was somewhat of a disappointing result. So it was fun, but it was sort of a null result. But there was a really great aha moment in this one. And this one I was really excited, but it failed again. When you mix the blob, the figure on the left shows an ozone hole, first dashed lines, the outer ones, being slowly squeezed and compressed and sheared as it disappears into the background. And so that's typical. The scale's in meters. This is a molecular strain diffusion model. We're getting down to the meter scale. And then what happened at the right was really exciting. You actually got separation of chemical families in the atmosphere by having large gradients. With one side, you had one species that diffused quickly, and the other side, you had another species like bromine nitrate that diffused slowly. Then you actually collected on one side of the gradient excess total bromine. So you actually were able to separate out chemical families because you had differential diffusion in the stratosphere. And this was really exciting because it meant we could actually get around the idea that the stratosphere is mixed and uniform and families were conserved. And you could actually have chemical systems which actually separated and collected things like ozone depletion elements like bromine. However, as usual, the minute you ran a little further, the wrinkle appeared and then it disappeared because the diffusion and strain made it all disappear. And so it was great fun. It lasted for a day, and then it went away, and it didn't produce any further ripples down the line. So once again, it was a really fun, exciting thing to see. You thought you discovered something great, and then you realize you did, but every time it happened, it disappeared. So it was another loss. We also lost Andrew Jaffe. He's now cosmology professor at University College London. He decided that this was too crazy. He was going back to astronomy. It was much simpler, much more straightforward. He wanted to be a cosmologist. So he's having good fun doing what he's up to. So the nonlinear nature of the chemistry from the point of view of what we're looking at, the multiple solutions between chlorine, nitrate, and nitrogen systems, chlorine systems, whatever, didn't go away. In 1983, Ralph Cicerone and Stacy Walters at NCAR noticed that for the first time that increasing chlorine levels up to 9 ppb resulted in nonlinear ozone depletion. Those curves on the right go from chlorine levels in the background of 0 to 9. And you went from 0 to 9 parts per billion of chlorine. And you see them starting to curve up. The different letters are for different mixtures of chemical and diffusion models in their sort of 1D. So they had this set up, and he was very excited. So they said nonlinear ozone depletion, because most people assumed that the chlorofluorocarbons, which we already knew were going to deplete ozone, everything to date was linearity. And so everybody assumed that chlorine CFC ozone depletion was linear. And so if we kept increasing CFCs and we didn't see any ozone depletion, there was no reason to worry because it was linear in response. So therefore, we're learning more about the linearity coefficient. So we followed up at Harvard, having great fun, decided let's push the chlorine levels up a bit. So we ran 16 parts per billion chlorine. Now at that point, the chlorine dominates the system and overtakes all the other chemistry, including the odd nitrogen system. It titrates away nitrogen, and you have a total system driven by atomic chlorine, and you get massive ozone depletion. So it turns out, if Ralph had continued, he would have found this also, but we found in the models that when chlorine gets high enough, you get massive depletion, and it's even at all levels in the stratosphere. So this was sort of an interesting one. It was great fun. 1984. The world was about to change, but it hadn't changed yet. Okay. The interesting thing that came out of it was that the EPA, look at the little asterisk, this is pre-ozone hole. Pre-ozone hole really means there was very little ozone depletion. There's almost none observed to date. We were expecting maybe ozone depletion when we got to 8 parts per billion chlorine, like Ralph's paper, mine or whatever. And the industry was not really expecting much. And the industry wanted to get rid of any bans on CFCs, and they'd persuaded Congress to override the EPA on the ban on chlorofluorocarbons as propellants. And they were about ready to go. And John Topping told me that he and John Hoffman, EPA, then grabbed my paper and ran with it and managed to basically preserve the ban, saying, you know, there are still dangers out there. We shouldn't be lax. We should not give up yet just because you haven't seen ozone depletion. Just because you haven't seen ozone depletion. So this is November 1984. And so this was still a threat of 2050. This is a threat way in the future, but a nonlinear threat, maybe an irreversible one, as we worry about climate change now. So that was a success. That was a good paper. We actually had some impact. It was fun. Now, this is an aside. About the same time, summer of '94, it's a very meeting in Feldafing. It was Dixon Butler organized it from NASA headquarters and got many of us to go there. There were Europeans there also, but it was a big NASA presence. Sherry Rowland presented work that he'd done with his postdoc Sato, and they were looking at HCl and chlorine nitrate reactions, and they found that HCl and chlorine nitrate, which did not appear to react, they were semi-stable, there's no reason why they should react, appeared to be reacting, releasing chlorine gas. And he didn't know whether it was gas phase or on the surfaces. And that was an interesting talk, and it got everybody excited about what that could mean in Feldafing. And still we hadn't had the ozone hole yet, so it's 84. So this is the opening up of the idea of heterogeneous reactions. We came back and redid note, added, and proof in our paper, which was then in Press and Nature. Okay, and so we pointed out that if it really acted in gas phase, then the ozone depletion would be huge, 15%, even at near-term levels of chlorine. But we didn't think it was gas phase, but it was a note if it was that. We took pick the numbers sort of that cherry picked. But that turns out it doesn't really do it in gas phase. It does it on particles and on the surfaces. So then Farman, Gardner, and Shanklin upended all of stratospheric chemistry with the discovery of the ozone hole over Antarctica. It was clearly nonlinear. Chlorine had been increasing linearly. The sudden response of the ozone drop, the column of ozone over Antarctica, was really big. It implied there was a chlorine threshold for the ozone hole. And the fun thing about that one is Joe Farman's first references are to Ralph's paper and our paper on the nonlinearity part, which got him excited about it in the first place as to why he sort of went after the ozone, why he put this together and basically focused on chlorine. Now, a year later, there's a rush of papers to reaffirm the measurements and explain the ozone hole. There are a whole series of papers here. You can recognize various famous names and infamous names or whatever. There's dynamics, there's nitric acid, bromine, HOCl. They were all wrong, it turns out. So the whole first year of papers, which were all very famous for having gathered, all had mechanisms that, how we should say, they were probably torqued a bit. They may have had mistakes in the coding, they may have wrong J values, but they all end up reproducing the ozone hole due to mechanisms that really were not correct. But there's enough excitement that didn't matter. The key issue was there was chlorine and bromine there loose. The final paper that identified was the Molina in the lower right, came out at the end of all these, and that was that there's a dimer, Cl2O2, and that was the core cause of the ozone hole. It's the chemistry of the dimer, plus the heterogeneous release of HCl and chlorine nitrate on the clouds. So Sherry had started with the heterogeneous processing of HCl and chlorine nitrate, and it took a little while later before we actually found the chemical mechanism that would deplete ozone as quickly as it did. All of these depleted ozone, but never quite at the rate you wanted it to. So that was fun. I was able to stay out of all this mess, which is great, because I had just moved to GIST at the time, and I stayed out of all the warring parties that were trying to explain the ozone hole, and I found other things to do. I was then working on 3D tropospheric modeling. So let's do a math break. Let's look at lifetimes and timescales and leading up to methane, understanding methane. So rigor, back to rigor. Okay. The continuity equation is above. First line, it says the rate of change of some vector that you're measuring, some quantity you want, involves chemistry, transport, and radiation. They act on species differently, okay? And they can be different species, they can be different locations. And you set it up again as a Jacobian Taylor expansion. And if you work your way down, you find out that if you pick a perturbation that is an eigenvector of the matrix, the Jacobian matrix, then that third line down says that the rate of change of that vector is just the vector times lambda. And that means the bottom line, which is the critical one, the exact solution of the whole messy system is actually merely the initial vector times an exponential e-fold. Now, lambda can be positive, it can be a growing instability. Most all the ones we see are negative, meaning they decay. So that's the setup we want to look at. We're going to be looking at how systems have Jacobians that have eigenvalues, and the eigenvalues will have time constants associated with them. So we'll begin now with a simple example. We'll harken back to 1930, Sidney Chapman. This is the simplest example of how rigor helps. Well, I hope I can convince you of that one. So we have the Sidney Chapman mechanism. Molecular oxygen photolizes to two O2s, atomic oxygen. They recombine to form ozone. Ozone can photolize back to give atomic oxygen and back and forth, 2 and 3 cycle. And then finally 4 is the oxygen and ozone recombine to get you O2 back again. So Sidney Chapman came up with this fairly simple chemistry to explain the whole ozone layer in 1930. He was the theoretical modeler at the time, as opposed to Dobson and the other people who were measuring the ozone column. So this is our rate. I put in numbers typical of 42 kilometers, typical average rates. And so we'll look at a solution around this, for a single sort of box. We have 3 continuity equations. They're the rate of change of the 3 species. Okay, and so the rate of change of ozone is the production of ozone minus the loss of ozone. So again, you can look at the rates up, they're numbered up top, and you can put them all together, and you can solve this system very simply to get an exact answer. So now, the Jacobian, what's interesting is now you can set up the Jacobian of this system, and this is the 3x3 matrix. The 3x3 matrix will have 3 eigenvectors, so there'll only be 3 chemical modes for the system. There will only be 3 time constants for the system. So now the question is, what would you pick as the time constants? And for, I would say, many years in the 70s, we were arguing about what was the time scale for ozone to change in the stratosphere. Was it, photolysis time? Was it whatever? So there were all these fights going on with various people about how to define the time scales for ozone change. Now, they're all defined in this way. You take the amount and you divide by the rate. So if you take the time scale for molecular oxygen would be oxygen divided by the photolysis rate, which would give you 176 years, which is about the time it would take at 40 kilometers in the stratosphere to photolize all of the molecular oxygen. That's about right. Then you have photolysis of ozone. Again, timescale for ozone against photolysis and other reactions, and you end up with 12 minutes. If you look at atomic oxygen, it's 1.4 seconds. And we do our odd oxygen, where we combine O and O3, and we end up with 1.5 days. And if we look at total oxygen, all told, it's 0, because the system conserves O plus 2 times O2 plus 3 times O3 is a conserved quantity, because the oxygen is not disappearing from the box. What's interesting now is the Jacobian, however, he actually solved the system mathematically, gives you a very clean solution. You get the zero time, the infinity, effectively the zero time scale, zero, because total oxygen is conserved. You get the 1.4 second time scale because that is the fastest time scale of atomic oxygen recombined. And you end up with 0.74 days, which is similar to the odd oxygen time scale, but shorter. And the other time scales of photolysis of ozone and O2 just disappear. So the whole system really has only 3 time scales, 3 modes and 3 patterns. And that third pattern really looks like the odd oxygen, which is the relative change in O plus O3 together. So we never really did this in the 70s and 80s. And we had the silliest squabbles over time scales and whatever. When you think about it, it's rather silly. So if you do linearize the system and solve it correctly, you end up with something fairly simple and straightforward, and you get rid of a lot of various odds and ends. So let's move on to methane now. Dieter Ehalt was truly inspired. This original paper, The Atmospheric Cycle of Methane. He identified methane and the critical components and how methane cycled with hydroxyl radical, carbon monoxide, and molecular hydrogen. And those molecular hydrogens in here, and it's coming back again, so we consider hydrogen economy. And so now we're going back to the importance of the H2 in this whole system. So this was 1973. It's not a lot. People worked on it for a while, but they, so this is sort of what the system looks like if you want to think about what the chemistry is doing. We have the hydroxyl and HO2 radicals in the middle. They interact back and forth. They will react with the red circles, which are carbon monoxide, messy volatile organic carbons, nitric oxide, and they will then alter the greenhouse gases, which are ozone, methane, hydrofluorocarbons. So this is sort of the reaction with the greenhouse gases, okay? Now, that's when Thompson, Cicerone, Isakson, and Hove also started putting out papers following up on the Ehalt one, 10 years earlier, and they started doing more detailed modeling and more realistic modeling, better chemistry, and putting together issues about trends and what's happening. Now, what's most interesting in this one was Ivar Isakson and Øystein Hove. They pulled together a 2D tropospheric chemistry model, and they actually were running effectively, assessment type calculations. They put in a flux of methane. They'd ask what happened. They asked what happened to all the species there, ozone, OH, CO, so on. And what they found was an unconventional result that if the methane flux increased by 1.05%, the methane abundance increased by 1.5%. And so the tail on that one is when methane goes up, it's a sink for hydroxyl radical, as you saw previously. So OH goes down. When OH goes down, methane jumps up even higher because it's the sink for, so your methane, by increasing methane, you actually reduce the sink. You basically suppress the loss rate. And then it also drives ozone up. So this was an interesting cycle. And the Isakson and Hove paper comes up with the fact that there's something funny going on in an increase. Meanwhile, the 1992 IPCC, which is an intermediary copy version, still stays fairly mainline. You see outlined, it was not possible to quantify accurately indirect GWPs. There were worse things written, short-lived gases, GWP made a little practical. The concept that short-lived species have only short-lived climate forcings was prevalent then, and I even helped write it at the time, because that's sort of what I believed, 1992, little did I know. So there was a feeling that, NOx or something could have a climate impact, was going to be short-lived because it only lasted about a week out there or less. So this was sort of the climate assessment at the time. Now, then a new wrinkle came in. 1993 in Boulder, there was an alternative fluorocarbon, environmentally acceptable substitutes. It was a way for the chlorofluorocarbon and chemical industry to try and find something to get away from the compounds that were banned as ozone-depleting substances. So it's a big ozone meeting, and it had all sorts of talks, including one on climate. And so Don Fisher, who's DuPont scientist, presented results from his 2D model for modeling methane perturbations. And it was actually, full of chemistry model in the stratosphere, troposphere, and he modeled the methane. And so what he discovered was if you put a pulse of methane in, his model had, say, a lifetime of 8 years. So he'd have expected the black curve on the right to be a decay of 8 years, an E-fold of 8 years, for the decay of the perturbation. Instead, he found it was 12 years. And people said, well, that's funny. You must have botched your model somewhere, done something weird. And the first, and the response was, well, you just put too much in. It's nonlinear. First response was, it's nonlinear. You put too much in. So the concept was, if methane had nonlinear chemistry, as an easy extended hub, if you just put too much in, you change all the time constants. Okay, and Fisher's claimed that it really didn't matter whether you did 1, 10, or 100 ppb, you got the same answer and the same result. And everybody shaking their heads and decided that was Fisher's model, not to worry about it. And I remember talking with Doc C and some others about this, and I just couldn't get our heads around it. So I went back and beat my head against a wall, and finally came up with an understanding about what was going on. First paper was, I managed to barely get it out in time for the IPCC because the 1995 IPCC used it. Look at that. And the second one was a better one about runaway growth. So finding out how methane changed, how methane, CO, and OH changed the timescales of the system. So that was a good point. That was an aha moment. So the system that I built for the GRL paper was fairly simple-minded. It was a one-box model of the troposphere. It had CO, hydroxyl radical, and methane. They reacted. There was continuity equations down there listed below. You can see them. Okay. Then we put in numbers and sources to get about the right answer for the troposphere. So there were sources of methane, CO, and OH, and ended up giving us about the right mean values for the troposphere. So this is a regular simple model. It's sort of an average box model for the troposphere for OH, CO, and methane. So we take the Jacobian of that system, and this is it written out explicitly, okay? And the values look like this. So it's a matrix, it's got 1, 0, the rest have various numbers. The diagonal elements are the ones you think of as the timescales. That's sort of like the loss, inverse loss frequency for the species. So the diagonal elements are effectively minus 0.1 per year, which means it's 9.6 years for methane. Minus 4.17 is about 3 months, which is about the lifetime for methane, 3 months, a quarter of a year. And finally, OH is very rapid loss, about a second. The problem is when you do the eigenvalues of the system, the 9.6 years becomes 13.6, and even the 3 months of CO becomes 4 months longer, okay? The OH does not change. And the reason that all these things change numbers down the diagonal is because when you basically, to get the eigenvalues, you have to basically diagonalize the matrix. And those upper terms that you see that I've circled are involved from the Jacobian. They're the ones that basically change the diagonal elements when you run it through a QR algorithm solver that diagonalizes and comes up with the eigenvalues. If those were missing, then there would be no difference. The timescales of the system would be exactly the ones along the diagonal. They would not involve coupling with the other species. So what does it mean? It means more than just you have this funny timescale. It means that all species couple because they're not orthogonal. So if you actually do a perturbation to methane alone, it actually changes all 3 modes. And so you see, for example, if you change methane by 1 unit, you'll change methane, and it will create a perturbation like the one on the first line, in which 99.5% of it decays with 13.6 years, but 0.5% decays with about 4 months. And so likewise, CO will be excited and so will OH. Well, you're only worried about methane because that's the main species, that's the main greenhouse gas. And so to first order, it's 99.5% of it has this 40% longer time scale. And that's sort of important then for climate impacts. But what's more interesting is the indirect greenhouse effect. If you just perturb CO and you put a vector in of 1 perturbation to CO alone, hit everything. CO gets excited in both modes, methane appears. So 99.5% of the CO stays in the 3-month decay, but 0.5% decays in 13 years and sticks with the methane. What's interesting is the methane starts at 0 perturbation because you only perturb CO, but within a few months, you have about a 15% perturbation is revealed, and that decays again with a long time scale. So what you've done effectively is recognize that the ability of any species couples across all the other species. When you do a perturbation to a single species, you will generally see it unmask everything and kick every single time scale in the system. Now, so how do we understand Fisher's paradox in ways people understand it? And this was difficult to do because I had to try and explain it to my various colleagues in the IPCC of whether we could do this or not, or whether they'd accept it. So the idea is, if you add 1% methane, the hydroxyl radical changes by at most less than 1%. So the methane still decays with about 8 years. So people cannot understand why then we get a 12-year decay on the system, because the methane you put in has to decay in About 8 years. Well, if you actually color tag the methane, you add the methane in red. That methane is color tagged if you could figure out how to do it, okay? Then it basically perturbs OH at a small percent, but it decays with an 8-year E-fold. So it decays quickly. But what happens is because it was put in, the OH goes down and the original methane, the background methane, the green line, goes up. So you're already driving a system that has, say, 1,750 parts per billion methane, and if you put the new stuff in, the background rises. And effectively, the combination of those two gets you the one way to describe E-fold. I tried explaining to my colleagues, here are the equations, believe them, and believe me, it did not work. Atmospheric chemists were not, some of them were not exactly rigorous at the time. They wanted the feel. Anyhow, why does it not work for other species? Well, if you do carbon-13, for example, it's a very small component. So if you take 1% of carbon-13, that's 90 times smaller than 1% of methane. And so your OH change is extremely small. So that 1% change in C13 changes OH by less than 1/3%. So you won't see the perturbations on smaller species. It works because methane is one of the dominant sinks for OH. And if you put in 1% methane, you really do kick OH by 1/3%. So thereafter, we finally got the eigenvalue acceptance was accepted. Okay. You notice here it's written up the concept of adjustment time for perturbations has been applied to GWPs in this assessment. And therefore, basically, suddenly in 1994, the impact of methane on the climate is increased suddenly by 40%, basically due to the eigenvalue analysis. And so it's quite sort of a large change because people are now, most papers are worried about 5 or 10% changes in these effectively climate metrics. But this was probably the biggest change that we've had in a long time, except for identification of new feedbacks or new species. Sorry. Okay. Another thought is the Wrinkle really doesn't have to be nonlinear chemistry because methane and OH and CO is a truly nonlinear system. But we can have a simple linear chemistry, but it becomes interesting because of transport or other issues. So methyl bromide is an ozone-depleting gas. It's been pretty well known. That was a hot topic in the 1980s and 90s, in 2000s. It releases bromine in the stratosphere. The bromine in the stratosphere, which we'll call BRY, is a mix of compounds listed there. And bromine plus ozone and other reactions will actually destroy the destroy stratospheric ozone. So this is an important compound, but the chemistry is all linear. So the equations you set up are fully linear matrix. They're all those numbers in the matrix, the P's and T's, whatever, are constant values. So they don't rely on other species, but they are off diagonal because of the transport in the system. So we're looking at the diagonals being the local chemistry boxes, and then the rest of the matrix is filled with upper and lower triangular because of the transport and mixing of the system. That creates interesting things because once again, the matrix is neither upper nor lower triangular, but basically will then change the diagonal lines when you do an eigenvalue system. So what does it look like? Well, this is a simple profile of methyl bromide and BRY. Methyl bromide is going up from the ground. So this is 0 to 52 kilometers. It's a log scale from 0.1 to 10 parts per trillion. And so the typical values were 10 parts per trillion methyl bromide, and the estimate were being driven by 90 kilotons per year. And then the BRY comes out of the methyl bromide and then gets sucked into the troposphere where it gets rained out. And I put a little red circle on where the ozone loss is typically occurring around 20 kilometers. So this is the system we want to understand. It should be fairly simple. But what happens if you remove all emissions? Well, methyl bromide has a steady state lifetime on the left side, which is the burden divided by the loss of 1.75 years. And that's fairly straightforward in this model. It's not quite the best number, but it's close enough for this model. But when you release all the sources, it decays with 2.1 years. So it's not the lifetime, okay? Something's different. And the shape changes. So you'll note the red curves are successive decays of the methyl bromide that started with the blue curve. And every 2 years, every 1-2 years, you can see it shifting into this bull nose, where the last of the methyl bromide has to come out of the lower stratosphere into the troposphere to be destroyed. And so that chemical pattern is about 2.1 years, which is not the same as 1.75. That's okay. It was interesting enough, okay? But now something weirder and more interesting. We want to we want to calculate a damage function. So the damage function is the delivery of bromine to 20 kilometers in the stratosphere. If you get that bromine to 20 kilometers in the stratosphere, then it's going to destroy ozone. So we want to know what happens if you put a single pulse of methyl bromide, you dump it in the lower atmosphere, and then it gets up into the stratosphere, it releases bromine, it destroys ozone, and eventually it washes out of the stratosphere. So that equation, or the equations I have, is that BRY you see written up there. And you see it has all sorts of timescales for transport, and chemistry are sort of baked into all of those timescales. Okay, and you see a range of pluses and minuses. That means it starts at 0. So if you get just add up all the coefficients, you end up with 0. Why? Because at time 0, there's nothing at 20 kilometers. So all these equations with the exponentials, which are exact solutions to the differential equation, are then actually ways to ask and get the transport up. So it looks like the red curve below. Okay, so the red curve is what you see plotted with BRY, and you see it peaks about 6 years later, and it takes about 4.5 years to get out, more than another 10, 12 years to get out of the stratosphere. So this is a very slow, low amplitude, but persistent ozone depletion. So it's not a swift solution if you stop methyl bromide to stop ozone depletion. That was the rule on this was interesting. But now the interesting was this one, okay? The community always assumes that the damage function was the steady state lifetime times the steady state pattern. So steady state pattern has 0.42 parts per trillion bromine at 20 kilometers, and you have an E-fold at 1.75 years, so it's the product of the two. The red curve suspiciously came very close. When I did this, it took me about 3 or 4 days, because every time I did this, I integrated the red curve not as accurately as I wanted, and every time I integrated, it got closer and closer to the steady state curve. So I had more terms, I did more careful calculations, and finally realized that this was not an accident. This funny wrinkle is that no matter how you look at it, the steady state lifetime times the steady state abundance is actually equal to the whole transient curve. And then you're trying to figure out, well, what really is going on? So this drove me crazy for a while. And so then I had to come up with some other thought about how to do this wrinkle. So this is my other favorite GRL paper. It's one of the few that I consider to be a proof in atmospheric chemistry. Okay. This is 2.5 pages, 14 references, 30 days to submit from submission to acceptance. So I'm still pleased with that, but it's not great. Anyhow, it was still fun to do short papers in those days. So what is it? It turns out you can prove that the steady state pattern of damage, the steady state lifetime of the primary species, not the secondary or the tertiary, so it's the methyl bromide, not the other species, and the amount of the primary species emitted, the product of those three is exactly equal to the damage function, and including the rise and fall that you saw of the red line. And so it's quite an amazing result. And it says the steady state patterns and lifetimes are actually very important magical quantities. Now, I've begun to disbelieve them, but this one brought me back to the fact that they have some amazing features. So we have discovered the magic of steady state. This was a eureka moment. It was great fun to do this. We moved on to more difficult and tedious stuff. Juno Su and I worked on for several years on getting a 3D global atmospheric chemistry model up and running that included stratosphere and troposphere coupled. And it could run for multiple hundred years. And so what we wanted to do with this was to actually run decay patterns. We wanted to actually throw a perturbation in the model, have a full 3D model run through it, run through an annual cycle over and over again, and then look at the decay curve. So you see on the right, for example, a 200-year decay curve of a methane pulse. That's the red line. So methane's decaying fairly quickly. This goes out 200 years. And then you see N2O rise in response to methane perturbations in the stratosphere. And then the N2O decays with about a 108-year timescale. And then eventually you end up with a methane N2O coupled at the very end. And so this was the thing we wanted to do. It was fascinating because we actually, for the first time, demonstrated in a fully coupled model the link between stratosphere and troposphere in terms of chemical coupling. It was difficult to do. We could do it because the model was optimized for it exactly. No one else could do it at that time, and I think no one else has bothered since. I think they find it cute but not relevant. But I think it is one of the interesting tests they were able to pull off. And so anyhow, I found it delightful and pleasing that it worked. And to be able to see a 200-year E-fold in a 3D model was a very nice feeling. That meant we actually built it right and had the answer. So this one, what are the implications for the N2O and methane coupling are fun. N2O has a mode time scale decay time that's less than its lifetime. whereas methane has one that's longer. Methane perturbs OH and therefore has longer lifetimes, less loss. N2O depletes ozone. When you deplete ozone, the hard UV comes down, destroys N2O more quickly, so it has a more rapid decay for a pulse. And this was sort of fun. People have done that. The first calculation people have done. The second one, the methane N2O, no one has bothered looking at too hard. But we found out that the methane in response to N2O basically further reduced the N2O climate effect. So the chemistry base had an effect of changing nitrous oxide's greenhouse gas impact by about 12% downward. It basically makes it a less effective greenhouse gas because N2O depletes methane, which is a greenhouse gas, and it decays way much faster than most people think of its standard lifetime. So that was at least fun. We got a little surprised there. Again, not a big one, but felt it's sort of nice to find a result. It's intriguing and new that no one else has seen, even if they don't care about it, it's still fun. So let me jump to the future. This is the DC-8 taking off out of Palmdale, wheels up. You could argue that a DC-8 built in 1969 and acquired by NASA in 1985 is not the future, but for atmospheric chemistry for the last several years, it really has been the future. It's one of the best things they've got, and it is falling apart, and they're figuring out how to replace it. So there will be some future in this. So what does the atmospheric tomography mission do? The atmospheric tomography mission flew 4 loops around the globe. You can see the tracks up above. 2 of them went into Antarctica airspace. They all profiled between 0.2 kilometers over the ocean, about 500 meters, and about 12 kilometers. So the plane's constantly going up and down like a yo-yo and profiling the whole atmosphere and building a picture of the chemistry of the atmosphere in terms of variability and structure, and in this case, detail. So the key part about ATOM was not just to sample everything, but to sample everything in a way that you hoped you got what you wanted, and that's to list all the species we thought that were relevant for calculating the loss of methane and the loss of ozone. So this is all the list of species in most chemistry models that in a background environment like the oceans, which is 70% of the globe, this is what's driving the chemistry and driving global budgets. So we can take those with some simple kinetics and some cloud modeling, and then we can convert them into what we want to see, which is production of ozone, loss of ozone, and loss of methane especially. Now that means we're actually measuring, if you're willing to accept the kinetics and the modeling of the clouds of photolysis, which we did this with 6 different models and found the results were pretty similar. So we have some faith, there's some uncertainty about 10%. But effectively, if you measure all the species, they tell you about the future of that air parcel and about what it's going to do to methane and ozone. So we're actually then measuring kinetic rates, which has not really been done before, and you could argue it's still modeling, but it's the first, shall we say, semi-empirical rates. So what did we get? This is a profile. Down the Pacific's on the left, Atlantic's on the right. This is fairly recent stuff. We calculated this is loss of methane, so we'll focus here on methane. Loss of methane is sitting there, and you can see the hot spots are in the northern tropics. This is August for Atom 1 flight. These are a whole about 30,000 10-second air parcels that are combined to get these. Okay, there's high variability in small spaces, yet there's large-scale structure. Probability densities, when you put these together, are actually similar to what the models get. And you find out that 10 to 20% of the parcels control most of the reactivity and most of the budget, which you'd expect by looking at this. So the loss rates vary from blue, which is less than 0.5 part per billion per day, up to red, which is 3 parts per billion per day for methane. So this is the individual loss rates. So we actually get a methane budget if we can combine this, and we think we have enough statistics from the aircraft flight. And this is sort of new and quite interesting. So we actually have for the first time constrained budgets, which we can then use against the models. And it's sort of a new era, I think, in terms of atmospheric chemistry measurements. Now, remember we had methane feedback. We had the methane changed its lifetime. The methane nonlinearity with OH resulted in a change in OH, which then changed the lifetime of methane. And this is very important feedback and all the models I'm doing, but we've never had a chance to look at it. Do we have any results from the measurements? So this is the first look at this from the measurements. The top line is actually the feedback factor of methane. And what you see is that the feedback factor, which is effectively the d log loss over d log methane, which is about 0.7 on average. 0.7 means that the OH dropped 30%. So normally the loss would be 1 to 1. In this case, you have 7% loss of methane for a 10% increase in methane. So we can do this with the ATOM measurements. And we find surprisingly, and this was a shock when I first saw it 2 weeks ago, that it's uniform. You look below and you see the rates and the high range rates in the loss of methane, the hot spots, the not so hot spots, the really cold spots. And you'd think that the feedback would be variational with the activity. And the answer is it's not. It seems to be something very fundamental and seems to be the same over a huge range of chemical species and reactivities. And this one's sort of a surprise. It opens up a new way to test the models, I think, and it gives us sort of an observational constraint that we've never seen before. So we have something new in methane feedbacks, and that was sort of fun. That was only 2 weeks ago. So I would say what we've learned in some sense, we have a chemical characterization of the atmosphere opens up a new window on studying the chemical feedbacks and budgets. I think it's the first time we've had such a detailed speciation of all the chemicals in a parcel of air and pulled it all together. And that's what we tried to do in ATOM, and that was the original design, and it worked. So thank you. We've gone through a various wrinkle in time, and hopefully we're moving into the future. Appreciate it. Questions?
Okay, thank you very much, Michael, for that look at wrinkles and smoothing those wrinkles. And go ahead and put your electronic hands up or type into the chat if you have a question or comment for Michael.
Can you read the chat? I'm not sure I can.
Yeah, I can. So I'm looking in the chat.
Good. Okay,
If anyone
good.
has anything there or hand raised. Yeah, Francois.
Hi, Michael.
Hello.
I have a question about the first modes at the beginning for the nonlinear system.
Mhm.
We had timescales that were a few months and some that were like 9 years.
Yeah.
And on those timescales, you would think transport of the atmosphere would be important. I mean, in a few months, you mix within a few latitude bands, and in a few years, you mix the whole atmosphere. So did you ever go back and revisit those particular reactions with transport?
They're done with the full 3D models, both ours and others. Okay, and the same thing happens. Now, the box model is tuned to be a sort of atmosphere, but the concept of the modes being longer, 12 years instead of 8, have been shown by almost any chemical transport model, full 3D. If you have time-varying meteorology, it wiggles a bit, but it's still there. It doesn't really change it. It's a fairly robust result of the fundamental chemistry. That's all I can say on that one.
Okay, Michael, you mentioned the future and follow-up. I'm wondering if you could do the next generation ATOM. Did you really get everything you wanted, all the measurements and everything, or what would you add if it was happening again?
The ATOM mission was such hilarity. We started with a very tight, lean mission, and the camels got their nose under the tents very quickly. I'll say the aerosol people were the most effective camels for sneaking their instruments on the plane, saying it wouldn't cost us anything. Of course it did, but we got some really good stuff on aerosols. I don't know. I think we do need to worry about pernitric acid because the Caltech instrument was a little bit noisy, but it's probably more rule it out rather than it's going to be exciting. I think what we need to do now is start moving closer to the continents and looking harder at the plumes. And so it turns out we have a lot of similar results from the Chorus and Ferex DC-8 with almost similar instruments. And we can try the same kind of analysis and modeling we did for those and find out what's missing. And so it could be done. The reason for doing this was the middle of the oceans are still the biggest budget terms for anything, except production of ozone is probably important in the lower boundary layer of the continents, as important as the oceans, but in terms of loss of methane, loss of ozone, the oceans. And so this was still the prime interest. I don't think we missed much. I think the issue will be analysis to find out how repeatable it is, how do you get the statistics you want, because in the long run, we have to make measurements that work in chemistry climate models, not ones that just exactly match this meteorology and go back and simulate your aircraft flights. You really want to build statistics so that we trust the chemistry climate models, because those are the ones we're living with to basically make policy decisions for the future.
Okay, thanks. In the chat, a lot of thank yous to Michael and a lot of enjoyment of the talk.
I want to say thank you all for being here in the round room.
Yeah, I think you
So,
we've got a great audience turnout for today. That was great.
yep, there it is. You can see the
And
audience turnout.
a transition back towards the in-house.
I hope this is the
speakers
beginning.
there.
I sure hope this is the beginning of getting our masks off and seeing you all around here.
Okay, and
I will wear a tie if you're in person too for you.
Eric Saltzman is asking what other components of the Earth system should be paying attention to the Jacobian approach to timescales, ecosystems, clouds.
The carbon cycle, we've already started doing that because they have an impulse response function. Fortunately, uses original sort of box diffusion model of the ocean for carbon uptake was remapped onto an eigenvalue system, basically. So it has a series of exponential decays, which is what you think of as the response function for anthropogenic CO2. So that's done that way. The real issue is the combination and mixing. I do think the methyl bromide turned out to be most interesting because it's mixed between the methyl bromide and the boundary layer of the ocean where it's being made and destroyed. And then the issue is that when you remove the anthropogenic source, more comes out of the ocean. So I think the coupled systems and the timescales get very interesting. One of the things that's hardest to get across to people is that the eigenvalues and the timescale of the system are a property of the system as it is. They're not determined by how you perturb it. But the steady state lifetime is not a universal quantity. It's only a quantity based on where you emit it. So if I emit nitrous oxide at 50 kilometers in the stratosphere, the steady state lifetime you calculate would probably be about 2 years, 3 years. If I emit at the ground, it's over 100 years. So where you emit compounds and where you dump them in makes a big difference. I'm certain in BGC systems, the same thing will be true and could be quite interesting.
Okay, well, again, thank you, Michael, for that wonderful talk. And that's it. We'll be back again next week for our last seminar for this quarter. Thanks again, Michael.
Thanks a lot.